Okay, good afternoon. Welcome to the lectures. So, as usual, let's recap what we have learned on Wednesday, on Monday. We start chapter 4 last lecture, and then first of all, we have the process classification, right? And then we understand that it can be a continuous process. The classification 1 is continuous process, batch process, or semi-batch process, okay? Or steady state process, or transient state process. That's classification 2, right? Okay? And after that, we know that the general balance equation. Okay, can anybody tell me what's the general balance equation? 0.5. Early bird, 0.5. Anybody want to tell me general balance equation? Raise your hand. 0.5, yes, please. Okay. I'm sorry, I can just give you 0.3 points because you have the input minus consumption plus generation minus output equal to accumulation. Okay? Okay, but you can also say that minus accumulation equal to output. Okay, that will be also okay. But anyway, thank you for your answer. Okay, so and then after that, because we know this general balance equation, so we want to simplify this general balance equation. There are two conditions. Anybody want to tell me? How can you simplify or remove some terms in the general balance equation? Anybody want to tell me who is talking now? If you are talking, that means you want to tell me, right? Okay? No? 0.5. Anybody want to tell me how can you remove some terms in the general balance equation? I told you in the previous lecture. I'm sure you know that, but you just feel you are shy to raise your hand, right? Anybody want to tell me 0.5? No? This is very easy. You have nothing to lose. I don't deduct your points. Anybody want to tell me? No? Okay. If the process is not involve any chemical reaction, so the input, so the consumption, you can remove the terms of the consumption and generation, right? So the general balance equation will become input plus minus accumulation equal to output, because you remove the terms of the consumption and generation, right? Okay, this is condition 1. How about condition 2? What else you can which term you can remove under some conditions? Anybody want to tell me? 0.5. 1 point. 1 point. No? Yes. Okay, thank you. But I'm sorry, I can just give you 0.3. This is not the answer I want. But anyway, thank you for your answer. You can answer me in Chinese, okay? But you will be very welcome to talk to me in English, okay? So I give you 1 point. Can you not tell me which term you can remove under some condition? 1 point. You have to think. You will regret in the last lecture in this course, say, well, if I answer today, I get 1 point, so I don't get fail in this course. Okay, so 1 point. That's very precious. No? No? Okay. So if this process is a steady state process, that means what? It's a steady state. Steady state means that it doesn't change with the time. And the process doesn't change with the time. That means you can remove the terms of the accommodation. Accumulation, not accommodation, accumulation. Okay, so if the process is a non-reactive process and also is a steady state process, so the general balance equation will become input equal to output. That's what we are going to learn in chapter 4. Easy. Input equal to output. That's it. Okay? Right. I'm sorry that nobody can answer my question, but I hope you get used to my lecture. I want to get you some points because you are early bird, right? You're early birds. So that's what I want you to know. Anyway, so now let's move to the sections 4.3, material balances calculation. How can we do the calculation? Every time when you have a set of a question, or when you have an exercise, you need to read the questions, like from a description of a process, and then after that you collect the informative data. You collect the data, and then you do a simple calculation. That's what we are going to learn in chapter 4. So I want to give you an example as give you this mixer as an example. Remember in the previous lecture on Monday, there are two streams going in. For example, you have 200 grams methane and this might be, okay, 150 grams of methane, and then with different proportion of the water, and then you mix it. You put these two streams into a mixer, and as a result, you got total amount of the mixtures, and then you got the percentage of the methane and percentage of the water. Okay, so this is what we are going to learn today. That's called flow chart. Flow chart is that as an engineer, you need to visualize the conditions, the situation what you are going to face. And then it can be the description from a person or people tell you what's going on, and you visualize or you can analyze the problems. And the good thing is that you have to make it as a kind of visualized, and you put the data, you put the numbers into this flow chart. So as a result, we have some elements. So elements is that this is called process unit. Okay, this is process unit. You can draw as a box or other symbols, triangle, whatever. But normally we use box here. Okay? And then element 2 is you need to have input and output. Okay, these streams or the lines with arrows. The line with arrows, you have input and you have output. Remember, chapter 4, we only talk about input equal to output. Okay, nothing else. And then after that, the element 3, you have to write down the values, right? Like 200. And you have to write down units, these grams, okay, and percentage. Okay? So these are the 3 elements. And I have some suggestions for you. Is that when you read the sentences, when you have some questions, you have to write down all the input and output, and then with value and unit. That's very important, because this not only for yourself to understand, but you also need to let other engineer or other friends to understand what you are doing. And the second is that you have to make a string and make an unknown here. For example, this is called unknown variables. For example, you have 200 grams and string 1, 150 grams string 2, and you have one output stream. And you don't want to write down something like this, because you want to use symbol, which is a common language and that you can communicate with others. Okay, so this is a common symbol. This is a symbol you can. Anybody knows. N stands for molar. If you have overdot here, Ni stand for overdot, stand for molar flow rate. X stand for mass fraction. Okay, so in this case, you want to write down something like this, Ni, and you know, wow, this is mole, or this is gram. Okay, and here you can write down Xi, or 1 minus Xi. This is fraction. So what you want to know is, what you want to do is write down all the information you know, and also mark the unknown with a certain well-known symbols, like N or M or X. Okay? So here is the example. For example, you have M equal to X, M2 equal to Y, X equal to 3Y. So M1 equal to 3Y, M2 equal to 2Y. So you don't want to use two symbols. What you want to use is only one symbol. Okay? And then this is what I want to tell you is N is stand for mole. N over dot stand for molar flow rate. V over dot stand for volumetric flow rate, or represent the volumetric flow rate. Okay, so this is the symbol, the symbol which you can communicate with others without any problem, because everybody knows V over dot is a volumetric flow rate. M is represent mole. Okay. Right. So let me show you an example. 4.3-1 humidification and oxygenation process. So I hope you still remember that this is one of the case you learned in the previous lecture. You have air fed into this hexane, and air come out with hexane. So there's about 10% of hexane in the output stream, right? So this is what? This is you want to deliver hexane in the gas phase. However, if you put the water into this place, into this tank, and you feed the air into this container, so air will come out with water. So this is called humidification. Or the machine is called humidifier, right? Remember I told you in summer, United States is very dry. In winter, Japan is very dry. So you need, well, I shouldn't say that. I stay in Tokyo, so I say Tokyo is very dry in winter. I stay in California, so I should say that in San Francisco, in summer it's very dry. I should say in that way. Okay, so you need humidifier. Okay, you need humidifier. Okay, and why you need oxygenation? Why you need to introduce oxygen? Why? Because you want to have output with water and oxygen. Why? This is one of the applications, the growth rate of the certain organisms. You know, some organisms need water and oxygen. I mean, high percentage of oxygen. Okay, require an environment of the human hair enriched in oxygen. Okay, this is case one. Case two is that medical use in the humidified oxygen. You know, as a patient which has a lung problem, he cannot breathe well, so he needs more oxygen. But you cannot introduce dry air with oxygen because it's too dry. Your lung cannot stand that kind of dry air. So you need to have high percentage of oxygen and water to feed into this patient. Okay? And another case application of this humidification of oxygen is called microbubbles. What is microbubble? This is a bubble in the water. You know, when you can make bubbles in the water, right? And you know, this surface area is too low because this bubble is too big. So can you have a machine to make a very, very small, tiny bubbles, which can increase a lot of surface area? This is called microbubble. So this bubble can have what? Oxygen. Oxygen. What's this for? You know, this is a shower head. You know, you use every day, and now you can buy this in the market. You can make a microbubble. So what is this for? You can clean your body well. You can clean your hair well without shampoo or without soaps. Because the surface area is very huge, and you can bring some dust away from your body. Okay, so this is very popular now. You can buy this in the market with a microbubble head. Okay, so let me show you what is microbubble. Good thing about microbubble, let me show you. Okay. So the example 4.3-1 is that you want to introduce water and oxygen and to the output. So this is called evaporator, right, which make the water evaporate faster, right? Okay. So we have a text here, but I don't know whether I should read this with you. I'm sure you have 资君立体 PDF file, right? You have this file. Okay, this is the first example showing you in the PDF file 4.3-1, the flow chart of an air humidification and oxygenation process. Okay, let's read this together. I hope you have that with you. Experiment on growth rate of the certain organisms require an environment of the humid air enriched in oxygen. The three input streams are fed into evaporation. So this is evaporator, right? Sorry, not here. So there are three input streams. You remember three input streams into evaporator chambers to produce output streams with a desired composition. So you have three input, one output. Okay, three inputs, one output. The first input is liquid water, fed at a rate of 20 cubic meter per minute. The second stream is air, okay, and they don't give you the information of the flow rate, no, but they tell you that air is 21% oxygen and 79% nitrogen. This is stream 2. Okay, the stream 3 is the pure oxygen and with a molar flow rate of 1/5. What's 1/5? 1/5, right? 1/5. Okay, of the molar flow rate of the stream B. So you have this is stream. This is if this is 1, this will be 1 out of 5, right? 1/5 molar flow rate of B. So this is the kind of condition. Okay, so this is the information you know, and the output gas is analyzed and is found to contain 1.5 more water. So they tell you that once you have output and you have 1.5 more % of the water. And the question asked you is draw and label a flow chart of the process and calculate all unknown stream variables. So you have some knowns, you have some unknowns. And then the question, this exercise asks you to find out all the unknowns. Okay? Right, so let me show you how we do in this case. So we have three streams. The first stream is water, right? So this sub L is represent liquid. So this is water, and you have 20 cubic centimeter water per minute and fed into this evaporator, or we call evaporation process, right? The second stream is air. They didn't tell you anything. There's no information, but what you know is 75% nitrogen, 21% oxygen in the ratio of mole. Okay, so you have an unknown. You don't know how many amount of the air fed into this evaporator. And listen, I always I always symbol this unknown in red color if this is unknown. So unknown always represent, the symbol marked in red color always represent unknown in my course. Okay? Right, you have stream 3, which is pure oxygen, and then we understand this oxygen has only 2%, 20% of this input. So you know that this is 20% air, like this. So these two unknowns are the same, right? Okay, so you have one stream out. So one stream out, as you know that in a sentence, you have 1.5% of the water in the output stream. And then you have unknown of the total output. And then you don't know the ratio of the oxygen and ratio of the nitrogen. So this is the unknown as you read the example 4.3-1. So I give all the information to you, and then this exercise wants us to find out the unknowns. Can you do this for me? Can you? Easy, because what? Because you just use general balance equation. And this is a non-reactive process, right? This is evaporator. It doesn't involve any chemical reaction. So you can remove the terms of the consumption and also the terms of the generation in the general balance equation. And also this is a steady state process because this is a continuous process. And continuous process represents steady state. So you can remove the terms of the accumulation. So as a result, general balance equation can be simplified as input equal to output. So water input, because of the conservation of the mass, water input will equal to water output. Oxygen input will be equal to oxygen output. Nitrogen input will equal to nitrogen output. So you have three equations. Okay? And you can solve three unknowns. You have three unknowns here, right? N sub air over dot, N sub total over dot, and Y here. So three equations, three unknowns. Bingo. You can get the answer of these three. Okay? Right. So I don't want to waste your time, so please do this by yourself. By the way, the important thing is this is 20 cubic centimeter. It's not mass. So input equal to output is also always represent mass only, or energy or momentum. It doesn't represent value input equal to value output. No. So you have to convert this value to become mass, or become moles, right? Because you have more input, more output. So can you do this for me? You know, right? Because you know the conversion factor of the value become mass, that will be density. Okay, the mass become more, the conversion factor will be molecular weight. So, as you know, the water of the molecular weight and of the water and also the density of the water. So you know how to convert 20 cubic centimeter to become mole. Okay? So again, I don't want to waste your time, so please do this by yourself. You can practice this, okay? So let's move to the section 4.3b, flow chart scaling and the basis of the calculation. What is scaling? Scaling means that this is the example. For example, you have 1 kilogram hexane, 1 kilogram toluene fed into this process. Of course, you have 2 kilogram out. And you have 1 kilogram, of course, you have 50% of the benzene, 50% of the toluene in the output stream. Right? So, you might say, well, Professor, if So as you can see, this is a batch process because it doesn't involve time, right? But if you, can we give a time in this process so we can use mass to become a mass flow rate? Yes, it works. Still the balance. Or can we change from a kilogram to be a pound mass? Yes, that's no problem. This is also balanced. And also, can we scale up? Can we make it larger from 1 kilogram to become 1,000 kilogram? Make it larger or make it small. That's okay. Okay? So, this is the things you need to know because you draw a simple flow chart so you can scale up, scale down, and change the unit as you like. And it's still balanced. Still, the equation of input equal to output still obey. Still can be used for this process. Okay, so this is exercise. If we scale up 300 times of this process, no problem, right? So from 1 kilogram to 300 kilogram. And of course, you will have 600 kilograms in output. And I'm sure you understand, the fraction doesn't change, right? Fraction doesn't change. Remember this? Okay, so can we give a common factor to both sides? Okay, yes, we can, right? We can give common factors like hours, like times. So it become, from a batch process become continuous process. Okay? Right, so no problem. Or you can change from the pound kilogram to the pound mass, right? Right. So let me see the scale of a separation process flow chart. Well, this is another exercise 4.3-2. I think I want to skip this process. Okay, can you change this from 100 mole to become 1250 pound mole per hour? Can you do that? Yes. From gram mole become pound mole. From the batch process become continuous process. Okay, so please change this by yourself. Do this, practice this by yourself. Okay, so another important topic in this section is you need to choose a basis. You need to choose a basis. For example, if you do an exercise and then you need to find out what is the basis. The basis is that you start from that point and you start to do the calculation. Okay? You might don't understand what I'm talking, but I'm going to give you some examples so it will help you to understand what I'm trying to say. So common factor, and then we know that, and then we can scale up, scale down. Okay, so if there's no basis, only ratios here, you need to give a basis. And then after that, you can do the scale up, scale down, or change the unit. Let me give you some exercise later. So this section 4.3b is the summary. Okay, so next is 4.3c, balancing a process. So for the total and the species balance, for example, we just give this as an example. We have a mixer, benzene and toluene into this mixer. As you can see, you understand this is 3 kilo, 1 kilo. So you have how many? You understand, right? Okay, so you know the ratios. So for these three are unknowns. There are only two parameters, two values you need to find out. Okay, but you can do the balances using total material balance, like total input equal to total output. Or you can use benzene balance or toluene balance. So you have three equations. You might say, wow, Professor, something wrong. Because You have two unknowns, but you can write three equations. That means you can solve the unknown. You can get the unknowns of the m and x. But why you need three equations? Why you need three? You don't need three because two out of these three, you can just use two out of these three. And actually, there are only two independent equations. Because this one is this plus this, right? So you have only two independent equations, 两个独立方程式. There's no three independent equations. Okay, only two. Okay? Okay, so the rules of the balances apply to the non-reactive process as you know that input equal to output, right? So, as you can see, there are only two independent equations. You can use these two, or you can use these two, or you can use these two. You all get the same answer. Of course, which one you want to choose? Which two you want to choose? You find out the easy way, right? Easy way to give you the less variables, and then you can easily to get an answer. Okay. Okay, this is exercise 4.3-3. Let me. I think I want to skip this. Okay, I think I better skip this because you already know this. Right. So this is, we already learned a lot of mixer, remember? So, you know, as a simple mixer, you can, like a cup of coffee, black coffee, you put the milk and sugar into the black coffee and you use a spoon, teaspoon, right, to stir the coffees. So you make the coffee with milk. But this is batch process. If you want to do it continuously, how can you do it? As an engineer, in the engineering way, this is called continuous process, a mixer. So you have an input, and then you have some plates, which is some certain angle. And then the water will go in, the mix A and B liquid will go into this place, and you will mix in this pipe and come out homogeneously. Okay, homogeneously. So this is a kind of continuous mixer. Let me show you. And you know, in the industry, you can do this. This is much faster, right? This is much faster. So I show you the. This is the mixer, continuous mixer. You see that? You have red ink, and then in order to mix this ink with water homogeneously, if you don't have this mixer, it takes a long time. Okay, you might use a mechanical way to do the mixing, but as you can see, once you have this kind of mixing, you can do it very quick. Okay, but you need to design the plates, the angles. You can even make it thinner, so you can do the modeling or do the calculation to make it quicker. Okay, so as an engineer, you need to think how to do the mass production, not do it at home or do it in a laboratory. Okay, you need to have a very big, you need to have a new way of thinking to design a continuous process. Okay? Right. So, I think before we move to the next topic, this is important, degree of freedom analysis. This is important, so I want to have a break first before we move to this topic. So today, let's play Kahoot now. Right. This is an important topic. Actually, this will be in your final midterm exam paper, and also it might be in your final exam paper too. So it's called degree of freedom analysis. This case, the case I just skipped, there are 3 unknowns, right? So in the end, we achieve to get these 3 unknowns by input equal to output. But what happens if I give you a more complicated questions? Then you want to start to do calculation, or you want to know is this problem can be solved or cannot be solved? Well, this is important because why? Before you do any lengthy calculation, you can use a properly draw and label flowchart to determine whether you have enough information to solve a given problem. So, do you have enough information to get these 3 unknowns? That's important. Okay, so this is a technique I want to show you today. So why? What's that to show you? That's called DOF, degree of freedom analysis. What the degree of freedom analysis is to verify or to justify whether this problem can be solved or not. Okay? So the procedure of doing DOF stands for degree of freedom. Okay? So in this case, of course, you need to complete all the information in the flowchart, including knowns and unknowns. Okay? And then you have to count unknowns variables. You have to count how many unknowns. For example, in this case, you have 3, 1, 2, 3 here. Remember, I told you that all the unknowns in my course is all marked in red color. Okay, this is red, so you have 3 unknowns. And independent equations. How many independent equations you can get? Because you have 3 unknowns, you need to at least have 3 independent equations. So 3 equations to solve 3 unknowns. This is simple algebra, right? Okay, so do you have 3 unknowns in this case? Do you? In this case, you might think, well, Professor, this is sodium hydroxide. Okay, and this is water. You only have 2 species. 2 species means that water input equal to water output. NaOH input equal to NaOH output. So you have 2 equations. But you have 3 unknown. Where are the another 1 equation? Or you cannot find another, or there is no another equation. There is no 3rd equation. You don't know. So you need to find out. And this is the technique I want to show you, that how do you get the equations. Okay? So let's say that if number of the degree of freedom equal to numbers of the unknown minus numbers of the equations. Right? You have 3 unknown, you need to find out 3 equations. If the DOF equal to 0, that means unknown equal to the numbers of the unknown equal to number of the equation. Problem can be solved, no problem. If the DOF larger than 0, that means unknown more than equations. So more unknowns than equation, that means what? The problem is unspecified, right? Or you have some you miss some information, and please find out the information. Okay? How about if the DOF is smaller than 0, that means equation is more than unknown. I just show you the example, right? You have 3 equations, but you only have 2 unknowns. Why? Because 3 equations, there are only 2 independent equations. Whatever. So the flow chart is incomplete labeled. So you might miss some unknowns you didn't mark. This is the first one you need to think. Or the problem is over-specified. There are some problems in this example. Okay? So, and now this is the technique to for you to find out the equations. Okay, for the mass balances, you have 6 directions to find out equations. For the energy balances, that will be in chapter 7, chapter 9, and forget about that at this moment. So first, there are 6 directions. The first direction is for the non-reactive species, you have mx equations, and then this is the numbers of the species. For example, in this case, you have NaOH, you have H2O, so you have 2 equations. So for the non-reactive species, you have 2. Okay? And for the reactive species, that will be in 4.7 section. I will tell you this later. Okay, so this is number 1. And number 3 is that, number 2, sorry, number 1, number 2, or number 3 is that the process specification. What is process specification? For example, in the exercise or in the questions, I tell you the relationship with the mass and the volume. That's what? Density, right? So this is called specification. So this is one example. For example, the acetone fed to the condenser. This is a condenser. Okay, N1. So this is called N1. Right? Acetone fed into the condenser. You have N1 here. And I also told you that the 40% appear in a condensate stream flow. So condenser, you have condensate stream, right? You have upstream and downstream. So condensate stream will be M2. M2 will be, so what's the relationship with N1 and M2? So 40% times N1 will be equal to M2, right? So this is what we call specification. So M2 equal to 0.4 N1. So this is the information you can get, and this is another equation you can get. Okay, this is number 3. So you can get specification. Okay, so another direction is physical laws and physical properties. Physical laws is what? So you know the density is a kind of density, molecular weight is conversion factor, right? This is physical laws or physical properties. Or you have this saturation or vapor pressure or equilibrium conditions. This will be in chapter 6. I will introduce this to you in chapter 6. So this is another information which is the physical laws. Okay, like vapor pressure or like like density, like molecular weight. And number 5 is physical constraints. Physical constraints is that, for example, the stream molar fraction is x, y, z. So there are 3 unknowns, but actually this is physical constraint because you know x plus y plus z equal to 1. So you can reduce unknowns from 3 to 2. And this is what we call physical constraints. Okay? Okay, so number 6, if this involves chemical reaction, you need to think of the stoichiometric relations. For example, this is hydrogen plus oxygen become water. And you know you have 2 moles of hydrogen and you will produce 2 moles of water. You only have 1 mole of oxygen, you will produce 2 moles of water. This is called stoichiometric relations. Can anybody tell me what is this? What is this? What is the application using this equation? Anybody want to tell me? You have hydrogen, you have nitrogen, and produce water. What is this? What's the application for this chemical reaction? 0.5? No? No? Fuel cell, right? Remember fuel cell? I told you when you are in the last semester, fuel cell. Hydrogen plus oxygen produce water and what? Energy. in the form of the electrical energy. Right? This is called fuel cell. 燃料电池. Okay, so anyway, we don't talk about this much except in the section 4.7. Right. So this is another, example, degree of freedom analysis. I want you to read this with me. A condenser here. What is a condenser? Condenser is, this is, we just learned humidifier. And another one is called dehumidifier, because in Taiwan it's too wet. The air is too wet. The relative humidity is reached to 70%, which is not good for you to stay. You feel very humid. So you need to have a dehumidifier at home, right? 除湿机, right? 除湿机. So you need to get dry air to let you feel more comfortable. Okay, so let's do this. Let's read the sentence by your. Let's read this. I hope I need you to have a textbook, or you need to have a copy of this so you can do this with me together. Okay, this is example 4.3-4, degree of freedom analysis. Okay, a stream of a humid air enter a condenser in which 95% of water vapor in the air is condensed. Oh, this efficiency is very good, right? So air, 95% of water will be condensed. Only 5% will be in the output in the air. So you feel comfortable. Okay? The flow rate of the condensate. The condensate is the bottom stream, right? The liquid leaving the condenser is measured and found to be 225 liters per hour. So you realize this is measured by liter or measured by volume. So you need to have what? You need to have a conversion factor to make it become mass, because input equal to output is always related to mass or mole. It's nothing to do with volume. Okay, so remember this. So dry air may be taken to contain 21% more oxygen, of course, right? With the best nitrogen. Okay, calculate the flow rate of the gas stream leaving the condenser and the molar fraction of the oxygen, nitrogen, and the water in this stream. So from here, this is the question. So from here to here, this is a description. So you need to make the description to make it become a flow chart. Okay? Okay, so let's do this. So you have a condenser. And normally you have a humid air, very humid. And you understand 95%, so you have two streams. One is liquid stream, right? At home you have 除湿机, there's a tank to have water, right? Liquid water. And you have dry air. But you don't want to have 100% dry because it's too dry. You don't feel better, you don't feel comfortable. You need to have some certain amount of water. Okay? So we understand this is the humidifier. So as a sentence, as the description tells us that you have 95% of water in the feed will be condensed in the liquid stream. That's what you know. And also, the container produce 225 liters per hour of the water in the liquid stream. That's the information you know. And then they also tell you that the humid air has a 21% oxygen. That's why you know. But you don't know, what you don't know is the amount of the humid air. Or in this case, it's dry air, right? And also what you don't know is the amount of the water in this. So humid air contains dry air and water, right? So you have N1 and N2. That's what you don't know. And the unit here is mole. Okay? Right. So So that's all the information you know. And then now the thing is you need to put the unknowns in this flow chart. Okay? So this one, you have to put all the information. Do you get all the information here? Yes, you do. Because you have the amount of the air and water. You have the fraction of the oxygen and nitrogen. Okay, how about this stream? You don't know the amount of the output, right? So you need to write down here. The M3 is the amount of water per hour. You might say, well, Professor, this is the output. Yes, it is. But this is volume. This is not mole. So you need to do conversion of the liter to mole. Okay? Right, and then how about upper stream? Upper stream is the M4. Upper stream is pure air. So you have M4 and M5. Oxygen and nitrogen. You might say, well, Professor, can I write fraction? Yes, it's also okay. But the problem is you need to find out this. And 6 too, because you have some waters in the upper stream, which is gas stream. So you have these unknowns here. Okay? You don't have any air in this part, but you have air here. Because this is liquid tank. So how many unknowns here in this case? 1, 2, 3, 4, 5, 6. Can you get the answer of this 6? Okay, let's find out. Let's find out. Okay, so there are 6 unknowns. So basis is 5. You need to choose basis. This is only the numbers, which is the liter or volume, whatever. Okay, this is the basis you choose the 225 liters per hour. And then you draw the flow chart as the description tell you. So you draw the flow chart. And then you label the unknowns. You have 6 unknowns. And then you have degree of freedom analysis. Number 4 is, before you do the calculation, please do the degree of freedom analysis. Why? Because you don't want to waste your time. If you do the degree of freedom analysis, think, well, Professor, I cannot solve this problem. And you just say unknown. You just say 无解, right? You just say, I cannot solve this problem. So you don't need to do any calculation. So, how can we do the degree of freedom analysis? Remember I told you there are 6 directions, but now at this moment, we just think of 4. So count the numbers of the unknown and the equations. So how many unknowns? You have 6, right? You have 6 unknowns. And how many equations you can produce? You can get from this flow chart. Let's think of this systematically. So first of all, how many species? You have water, oxygen, and nitrogen. So you can use input of the water equal to output of water. You can use input of oxygen equal to output of oxygen. So input equal to output. Input equal to output. So you have 3 species. So you can make 3 equations. What else? The number 2 is you need to find out another 3 additional relations, right? Otherwise you cannot solve this problem. You cannot solve these 6 equations. So number 4 is what? You understand this is a liter and you need to convert to mole. So as long as you know the density, as long as you know the molecular weight, you can create another equation. So this is equation 4. Okay? So the equation number 4 is this we call specification. This is the physical laws. Physical laws. Okay? And number 5 is called specification. Why? Because you understand the description tell you that there are 95% of the water in the liquid stream is from the input. So you can have N2 times 0.5 equal to what? N3. This is what we call specification. You write this in the sentence of the problem. Okay, so you have number 5. How about number 6? Because you have 6 unknowns, you need to find 6 equations. Can anybody tell me, can you find out number 6 equation? No, unfortunately, there is no more information. You can get the number 6 equation. So as a result, you cannot get these answers of this problem, or you can just get partially answer of this problem. Okay, before you do any calculations, do this first, DOF. So in your midterm exam, I want to see you do DOF first before you do the calculation. Otherwise, you just get some certain point only. Because I think you don't learn 100% well. Okay? So the df is equal to unknown and minus n equations. So you cannot solve this. Okay, so if I give you another specification, say if additional information given, human air contains 10% water, so human air contains 10% water, that means what? That means N1 plus N2 equal to times 10% equal to N2, right? Okay, so you can have number 6 equation. So you can get all these answers. Okay. Right, so this is the things you need to know. So this, you know, the condenser, why water can be condensed. This is a heat exchange. You know, you get water in and condense and they release and some heat exchange. So you can have some of the you can have a dry air come out. We don't talk about this is the energy balance. So we don't want to talk about this now. But what I want to tell you is that you know, we use this a lot in our daily life, right? Okay, so now the 4.3e is the general balance equation, general procedures for single unit process. So there are 9 steps. I want you to think of this step by step, so you don't miss any information here. Okay, so there are 9 steps. The step 1 is what? Step 1 is choose a basis. For example, in this case, which one is the basis? Which one? 100 mole, right? Because this got the numbers, you know. These are all the ratios. Okay, this got dimension. So this is the basis you choose. So you have to choose a basis. It can be here, it can be here, it can be here. But basically, it will be easier for you to do it here because this is the input. Okay? However, if there are many bases, you can choose one, or you can get a summation of this and make it become 1. Okay, so if there's no numbers like this, you make 1. You make 1. And basically you use 100 is easier because you have ratio and easy to do the calculation. You might say, well, Professor, I'm not happy, I just want to use 1 or 10,000. That's okay, it's up to you. Because you can do the scaling, remember? You can do the scaling. But anyway, 100 is the best one. It's a good one, I suggest. And step 2 is draw a flow chart. You know, according to the sentences, you draw a flow chart. This is a separator, this is a condenser, this is a distiller. So you can draw a flow chart. So fill in all the variables and fill in all the value variables and label unknowns. So you can fill in all the information you know according to the sentence you read, and you put the unknowns in the streams, which the information is missing. So you put unknowns. And label the variables for each process stream should be including either the total mass. So this is called total. You have this stream, right? You have this stream, and then you have to put this stream including two things. Or it can be one of these three. Okay, this is total mass. This is total mass, right? And then on the bottom of this arrow, you have fraction. For example, 100 kilograms NaOH plus OH, H2O, and you have fraction 20% of NaOH, 80% of H2O. This is one way to address this information. The second one is, instead of mass, you use moles. Normally, in gas phase, we use mole. In the liquid phase, we use mass, right? Okay, we also use the molar fraction. For example, 50 moles and 95% A, 5% B. And number 3 is, well, you are not happy with this. You just put all the, you don't want the fraction, you can put all the streams components. So you can have, for example, you can have 45 A, more A, and 5% B, 5 more B, something like this. Okay? Right, this is step 2. Okay, so if the things are unknown in this process, you have to mark unknown, as I just told you, right? So, and then the step 2, there's some information about step 2. More information about step 2 is, you don't want to get yourself trouble. You want to make unknown as less as possible. So if you have N1, if you have N1 and N2, and then if the description tells you N1 equal to 2N2, so you just remove N1, you have 2N2 and N2, that's it. So you don't you reduce the unknowns, so you can have less equation. Okay, don't get yourself trouble to make 2 unknowns, if possible. However, if the label volumetric quantities only they are given or you are asked to calculate them, so you don't want to use volumetric quantities, you don't want to use liter or cubic centimeter, because input equal to output, as I just told you, is equal input of the mass equal to output of mass. It's not input of the value equal to output of value. So you don't want to have value as a quantity in this flow chart unless the question asks you to do so, or the question provides this information to you. Okay, so we go to the number 3. Number 3 is write expressions for the quantities required. Excuse me. Okay, so you write down the unknowns. As I just told you this before, okay, already. Okay, number 4, convert a mixed unit to 1 basis. So this is the evaporator. Remember, there are 3 streams and 1 stream come out. And this stream is a liquid in the liquid phase. And then this is the value, this is the unit of the volume. So you need to convert the unit of volume to become mass or the moles. Right? Okay? So this is one of example. Let you please do this. Okay, number 5, which is most important step, is the step 5 is degree of freedom analysis. Okay, there are 6 types. Remember 6 types: mass balance, energy balance, process specification, physical laws, and physical constraints, and what? Stoichiometric relations. But in this chapter, most important here is mass, how many species, right? Specification, physical property, physical laws, and physical constraints. You need to think of these 4 points before midterm exam. Okay? And after midterm exam, you need to think of the stoichiometric relations. And for the energy in the chapter 7, I don't know whether I have time to talk about this to you or not, but anyway, I'll try my best to go to the chapter 7. Okay, again, material balance, process specification, physical laws, physical constraints. Okay, you need to find equations according to these 4 directions: 1, 2, 3, 4. Okay, from step 6 to step 9, step 6 is if the numbers of the unknown equal to number of the equation, like DOF equal to 0, that means bingo, you can get unknowns. So you list up all the equations and start to solve the equation. Right, number 7. Okay, you have a lot of, for example, you have 6 equations, and equation numbers 5, there are only 1 unknown, so you can get answer very soon. Okay, so you can get the less variables first, and then find the variables. And then number 7 is step 7 is get the answers. And number 8 is according to the requirement from the question, you might request, you might want to get fraction, or you might get value, you might get more mass, you might get more. Especially from value and fraction, you need to do, when you get unknowns, you might get more information about value and fraction. And number 9 is called scaling. Because if you choose the basis is not 100, it might be 123 or 5,394, for example. And then you need to do scaling. I will have a question example for you in this case. Okay, so let me summarize these 9 steps. Please remember these 9 steps. You don't need to repeat in your midterm exam, but this need to be in your mind. Step 1, choose a basis. This is, for example, in this case, where is the basis? This might be the basis, right? This might be the basis. Number 2, draw a flow chart according to the descriptions of the problem. Number 3, write expressions for the quantity requested, like this one. Okay, like the symbols marked in red color. Number 4, convert a mixed unit to one basis. For example, this is mole, this might be kilogram. So you need to do the conversion. Otherwise, you get yourself trouble. You might won't get the right answer. Okay, number 5, degree of freedom analysis. In order to find out this unknown can be solved or not. Degree of freedom analysis. Number 6, write the system equations and in an efficient order and solve. Number 7, check the solution. Number 8, calculate the quantity requested. You know, the question might be not asking you these 5 unknowns. It might ask you the ratio of this and this. The ratio of this and this. Okay? So you need to calculate the quantity requested. Number 9, do the final results, or we do the scaling. Something like this. So these are the 9 steps. Please keep this in your mind. And when you do the calculation, and you won't make a mess, or you won't get yourself trouble. Okay, so I think the example 4.3-5 is an example I really want to practice with you step by step. So that will be easier for you to understand or to do the calculation. So next week, Monday, I want you to have PDF file because I want to read the description with you, and then we want to draw the flow chart with you step by step. So you might want to print out the PDF because you won't, I don't know whether you can see the PDF and this PPT file in your pad or not, iPad or not, but I will have a book with me. So I will read a book, and I will, at the same time, I will draw the flow chart with you at the same time. So you need to work with me in this case. So what I suggest is have a copy of the PDF file before you come here. Okay? Right. Okay, so that's it for today. I hope you enjoy my lecture today. I hope you learned something from me. Now, before you go, and let's call the roll. 好，那要加分的就请过来哈。